All right, so we ended last time with the properties of an infinite series, right? And so now we need to talk about the nth term test for convergence. All right. So this is a really, really useful test because we actually did a problem like this yesterday in Village Hall where they had to prove that a limit existed and prove why, okay? And it wasn't the type of limit that you could just do the nth limit test for. It wasn't algebraically feasible. It had some factorials and stuff in it. So one of the things you can do if you're evaluating a limit, if it looks like a series that you know converges, then what you can do is show that the series converges. And if the series converges, well then we know that the limit to infinity has to be 0 because that's the only way a series will converge. So it was a kind of neat little backdoor way into proving that, to prove a limit. So this is not a small idea, but it's very simple, which is why I like it. So if a series converges, then its infinite limit has to be 0. So remember, that doesn't go the other way. If you take the nth limit of something and you get 0, that means keep going. Now you have to verify that it converges, right? Because we looked at the harmonic sequence and we saw that our harmonic sequence diverges, but its nth limit is 0. So, however, the reason you want to check for this, right? Because if the nth limit is non-zero, then the series diverges and you can shut the whole problem down immediately. So it's always a good thing to check on. Also, right? So let's write down what I just said, right? If the series, oops, my bad. If the limit of the nth term is non-zero, then you can just say right up front that the series diverges. So every time you catch one of these, if you actually check every time you catch one that diverges and shuts it down, it just really motivates you to keep checking because it's really nice to not have to work all the way through some of these tests we're going to learn. All right, so let's look at a couple examples. So if we look at the series from 1 to infinity of n squared. And you have to at least write the limit. You can't, like, just to justify this. So at the minimum, we say, well, the limit of this, clearly infinity. So the series diverges. So we don't even have to go any further. So let's look at another one. So this one, if we take the limit of this, any of you know what it is right away? 1. So the limit of this is 1, which is non-zero, so it diverges. So if the limit doesn't exist, if the limit's infinity, if the limit's non-zero. All right, let's look at another one. Well, we know what's happening here. This sequence just bounces back and forth between 1 and -1. So the limit of this just doesn't exist at all. You can't evaluate it because it never settles on a single value. So if the limit doesn't exist, right, it diverges. So I want you guys to see examples of all the different ways you can just shut a problem down right away by applying this idea. All right, we'll look at one more. All right, what's that limit going to be? -1/2. So non-zero, so we diverge. Okay, so the limit can be positive or negative. It doesn't matter as long as it's non-zero. If the limit doesn't exist at all, it diverges. And if the limit's infinity or positive or negative infinity, it will also diverge. So this is a really obvious thing to check for, and you're just kind of shooting yourself in the foot if you don't do it. And hopefully by this point, a lot of these infinite limits, we're hopefully getting sophisticated enough where we can just look at them and tell, right? So if you see a non-zero limit, I'm okay with that. All right, so now I want to do one of my favorite problems. I want to show you an actual application for the geometric series, something we can actually use it for, and you'll see why it's so useful. Good? Just keep copying, you're good. I write really fast. Okay. So this is actually going to be a real-world application for the geometric series. So if we want to find the total vertical distance a ball travels if each bounce is 3/4 of the previous one, right? So every time a ball bounces, the next bounce, it gets up to 3/4 of the height of the previous bounce, right? And we're going to let the ball start at a height of 6 feet. So I'm a visual learner, and whenever I'm doing a word problem or anything that's kind of real world example, I always recommend that you kind of sketch something just to verify and take a look. If you can do this problem without sketching, I'd be really impressed because there's a little bit of nuance to it, all right? So what's happening here is we have a ball that starts at a height of 6 feet, right? And it's going to bounce to the ground, come back up, and every time it comes back up, it's getting a little bit less height, right, than the bounce before. So this would continue to happen until eventually it's got nowhere else to go, and then it would just start rolling away. So we want to know what is the total vertical distance that this ball travels. So if you kind of look at this, you could also maybe see where you could do this with a spring. Right? If you have a spring that's slowing down, you can maybe want to figure out what the vertical distance that the object is traveling, because sometimes, like for physics example, we have forces that are non-conservative, and if a force is non-conservative, then you need to know the amount of energy that they use, and the amount of energy is actually path dependent. So you would actually need to know the vertical distance that it traveled to make sure you accounted for that properly. So what we're going to do is the first bounce, that makes this a little tricky, you only get half of a total arc, right? So we're going to call the first leg of this D1, distance 1. Then D2 is actually going to be 2 times this height, right? Because it's got to go up and come back down again. So then we'll just set up the first 4 terms, but we can see this will continue forever. So when you have a situation like this, where you know the multiplier of the subsequent thing, and that multiplier is less than 1, you're in geometric series territory. So if we could just turn this into a geometric series, because we don't know how many bounces we're going to have, we don't know how long this is going to go on, we actually have a formula for the geometric series which will allow us to just sum for the heights very quickly. So the trick is, how do you write this in the proper form? So we need to index from 0. We need to make sure that our R value is less than 1. It's clearly going to be 3/4, right? But let's look at what's happening. So if we look at D1, we know that that's just 6 feet because the ball falls 6 feet. D2 it's going to get up to 3/4 of 6 feet. So that's the distance for the ball to go back up. Then it's going to come back down the exact same distance. So these two add together and we get 3/4, 12 times 3/4. On the third bounce, we take the previous height of 6 times 3/4 and we multiply it by 3/4 again. So there's the distance for the ball to go back up, and then it's going to travel the exact same distance back down again. So we can combine these together. And then for D4, right, we multiply everything by 3/4 again. So you can kind of see now we're getting a pattern, and that's what we want to establish. So the total distance D that the ball is going to travel is we need to sum this stuff up. So we're going to get 6 plus 12 times 3/4 plus 12 times 3/4 squared plus 12 times 3/4 cubed, right? And this will go on till infinity if we want it to. So the 6 violates the pattern that we've established. So we don't actually have to include the 6 in our geometric series. We can simply form a geometric series for these terms and add the 6 on the outside, all right? But remember, to use that summation formula that we have, we need to index from 0. So that means when I generate my series, this needs to be the 0th term, this needs to be the first term, and this needs to be the second term. So if you're looking at the exponents in each of these, well, what you see is that the exponent attached to 3/4 is 1 higher than the value n that we need, because the geometric series, the first thing should just come out to be 12. So if I want to write this as a series, right, we're going to leave the 6 on the outside. I want to sum from 0 to infinity of 12 times 3/4, right? And I need the power that's generated to be 1 more than the n value that I'm looking at. So if I plug n equals 0 into this exponent, I need to return a 1. So we're going to index it with n plus 1. Then if I plug in a 1, it gets squared. If I plug in a 2, it's cubed, and etc. Does everybody follow that so far? Okay. So now that I've got a well-established geometric series, right, we're starting from 0, our R value is less than 1, we have an A, now I can just sum this up. So the 6 is still there, my A was 12, and my denominator is 1 minus 3/4. Oh, oops, my bad, guys. Hang on, I messed up. How did I mess up? What's wrong with it? What's wrong with the form of our series? What's the standard form of a geometric series inside? Go. ARN. Okay. So I can't just sum it using the formula because it should be AR to the n. And I've got AR to the n plus 1. So how do I fix that? Well, I can separate the 3/4 as 3/4 to the n times 3/4. So I can actually factor one of my 3/4 out front. So you got to be careful. These things are tricky. So if I pull the 3/4 out front, and remember, one of our properties of series is that you can pull a constant out front. Now we have a true geometric series. So now I can say 6 plus 3/4 times 12 over 1 minus 3/4. So that's going to give me 6 plus 3/4 times 12 over 1/4. And since I have in the denominator here 4 times 1 over 4, these cancel. And 3 times 12 is 36. So I get a total of 42 feet. So do any of you know what the golden ratio is? You ever heard of that? Sort of, yeah? right? So the golden ratio is this sort of magical number that crops up again and again and again, right? We see it in art, we see it in biology, we see it in nature all the time, all right? And what it is, and because it's a ratio, right, that means it's a fraction, and if you flip it one way, it's like 1.6 something, I don't remember the exact number, but if you flip the ratio upside down, you'll get a number less than 1, right? And so this isn't exact on everybody, but the golden ratio even appears like in the human body. So the ratio of the length of from your elbow to the tips of your fingers over the length of your arm, on average, works out to be the golden ratio. Same thing's true for your knee down to the length of your leg, right? Your belly button, which is actually your center of mass, that's when you're in the womb, right? Your nature wants to be efficient. So where your belly button is usually the center of mass of where your body like formed around that moment. So if you measure from your belly button down versus the height of your whole body, you'll a lot of times get the golden ratio, right? In nature, you'll see this like a snail shell, right? It's got concentric circles wrapping around and around in a spiral. If you look at the radius of the next circle to the previous circle, a lot of times you'll see the golden ratios there. In leaves, right, when the veins of leaves start forming down, sometimes you'll see that it forms the golden ratio. So another way you can apply the geometric series, right, it doesn't have to be the golden ratio. But let's say you're doing a problem where you have to like inject dye into a leaf because you want to photograph it and maybe look at what's going on with the veins. If you see a repetitive pattern like this, and you can actually measure what the drop down is from the first thing to the next thing, and you know it's a fraction that's less than 1, it will happen again and again and again and again and again, and no one wants to sit there and count and get a ruler out and measure all those individual things. But if you know that it's a repetitive pattern, you can form a geometric series and then sum up like the lengths of all the veins in the leaf, right? Or you could sum up, you know, the radius of the circles. You know, you can do different things like that. So it is a very, very useful property. It's a very famous mathematical equation, and it is used in all areas of science, okay? So this is actually the end of 9.2. So we're going to now start 9.3.